Hello, Cleveland Coding Society. I hope everyone's doing well and staying safe. Sorry we weren't able to be together in person for this year's Sink or Swim Symposium, but I'm thankful for the opportunity to still present in a virtual format. I'm Eric Broz. I'm a technical marketing manager with Lubrizol Advanced Materials for our resins and polymers portfolio within our performance coatings business. In this talk, we're going to be taking a look at high solids, waterborne polyamide-based polyurethane coatings. We're talking about some of the features and benefits this technology provides and comparing that against more traditional water-based polyurethane systems. Before we get into talking specifically about the high solids polyurethane dispersions, I wanted to take a few minutes just to provide some basic overview of polyurethanes in general and talk a little bit about what I mean when we say polyamide-based polyurethane dispersions. What we have here are kind of the basic building blocks for manufacturing a PUD. So what we have is a polyol or a soft segment that you're reacting with a polyisocyanate or hard segment. So you're reacting the OH groups on the polyol with the NCO groups on the isocyanate to form a prepolymer that you ultimately want to be able to disperse into water. So you need some type of a hydrophilic material, or in this case, acid, to help to disperse that material into the water phase. And then the other common ingredient used in the manufacture of PUDs is a diluent or processing aid, because in making these prepolymers, they tend to be fairly viscous in nature, so you need something to help cut down the viscosity and make them easier to work with. NMP was very commonly used as a processing diluent, and it kind of serves as a dual purpose, that it's both a great processing aid, very effective at reducing the viscosity of the prepolymers, and it also does a very good job at aiding in film formation when the coating is applied to the substrate. But over the last several years, NMP has come under increased regulatory scrutiny and is gradually being phased out more and more. So there are different diluents and processing methods more commonly used nowadays for making PUDs. And when we say polyamide-based polyurethane, what we're really talking about here is a new category of polyol or soft segment that Lubrizol has developed that I'll explain further in a few slides. Polyurethanes are segmented polymers or thermoplastic elastomers where you have alternating hard and soft segments. The hard segments are formed by the reaction of isocyanates and the polyols, and that hard segment is really responsible for cohesion of the material. The soft segments are typically a low Tg oligomeric polyol, and these are responsible for providing flexibility to the polymer. So you can see kind of this alternating hard and soft linkage. And the common soft segments in PEDs are typically made up of either polyester, polyether, or polycarbonate polyols, which we'll see on the next slide, each kind of have their own set of inherent strengths and weaknesses. And if you look at this on a percent by weight basis, the soft segment is the main component of the polyurethane structure. So because of it being a larger component, it really has a strong influence on both the chemical and physical properties based on the selection of that soft segment. So there are different types of polyols or soft segments that are used in making PUDs that are selected based ultimately on the various end-use performance requirements and properties you're trying to build into the resin. Kind of the main categories of polyols are the polyethers, polyesters, and polycarbonates. And you can see here they each kind of have their own sets of inherent strengths and weaknesses. The polyethers tend to have good hydrolytic stability, but poor UV resistance, so you wouldn't really want to use them in outdoor applications. The polyester polyols are kind of your general workhorse category of polyol, and they have good mechanical properties, good UV resistance, but they have poor hydrolytic stability, so they don't hold up well in the presence of water. And then the third category are the polycarbonate polyols, and these have good UV resistance, good hydrolytic stability, so they're higher in performance, but they tend to also be higher in price, and there's just not as many of them to choose from. There's limited composition variability. And then we have the polyamide polyol, which was previously believed to not be suitable for use as a soft segment, and there was no commercial availability. But Lubrizol has invented a new building block for synthesizing polymers, in particular new waterborne polyurethane dispersions based on these polyamide polyols. So I mentioned on the last slide that there was previously no commercial availability of polyamide polyols to use as a viable soft segment in making polyurethane dispersions. And part of that has to do with various problems associated with working with these polyamide oligomers. Some of these being that they have a tendency to form crystalline high melting structures due to a high degree of hydrogen bonding. And talked about how when you react that soft segment or the polyol with the isocyanate, that it's fairly viscous in nature. And so this even more so that the viscosity is usually too high to handle in a common PUD process. Then you sometimes have additional synthesis steps required to convert the amine or the carboxyl chains to hydroxyls so that you have that OH group available to react with the NCO group on the isocyanate and form a urethane linkage. The other challenge is raw materials just aren't as readily available. And then you have the potential for isocyanates to react with the amide group that in making polyurethane dispersions, I was trying to minimize the side chain reactions, whether that's with water or in this case, the amide, that you have a reactive isocyanate that you're trying to minimize these side chain reactions that could lead to some undesirable byproducts in your product. And then the other challenge being potential for moisture holdup issues. So there were many reports on attempts to make polyamide urethane polymers, but little commercial success so far. But Lubrizol's polymer synthesis scientists found a way to overcome some of these challenges working with these polyamide oligomers and develop polymers with polyamide segments. So ultimately, functional polyamides were developed with amine and/or hydroxyl terminations and controlled degrees of molecular weight, hydrophobicity, hydrogen bonding, and branching or rings. And really being able to overcome some of the challenges or misnomers and develop polyamide-based polyurethanes that are not impossible to process in any form. They're not water sensitive in that they would swell or blush at ambient conditions. In fact, we see them to have very good water and chemical resistance properties. And they're not brittle without any elongation or strength whatsoever. Polyurethanes are typically used in your higher performance, more demanding applications because of the properties they provide. And what we see with the polyamide polyurethane is an even higher level of performance over your standard polyester, polyether type materials. When we look at things like mechanical and chemical properties, we see that the polyamide provides very high levels of hardness and scratch resistance, as well as excellent chemical resistance properties, excellent water resistance. And then PUDs generally have pretty good adhesion to a variety of different substrates, but we find the polyamide provides some enhanced adhesion to sometimes more difficult to adhere to surfaces, things like nylon and other polyamides, as well as glass and polar surfaces. And then as we saw earlier, some of the inherent weaknesses of some of the other polyols, like the esters and the polyethers in terms of things like UV and hydrolytic stability. The amide provides better hydrolytic stability than the polyesters and better thermal stability than the polyethers. And then we find that the polyamide also provides very good UV durability as well. When we compare the different soft segments or polyols in a base PUD formulation, we can start to see how the polyamide really gives you some distinct performance advantages over the other available polyol types. And you can see in this spider diagram, when we look at kind of 4 key areas of performance, be it adhesion, stability and durability, barrier properties, and mechanical properties. And you can see there's a number of different things within each of those categories. While the other polyol types give you maybe some solid performance in one area, they tend to fall short in another, where they might have really good UV resistance but poor hydrolytic stability. The polyamide gives you, I would say, better all-around performance. You can see here, the more touch points you have on the outer edge of the diagram, the stronger the overall performance. So you can see the polyamide delivering very solid performance in things like chemical resistance, tensile strength, modulus, and hardness, adhesion to polar surfaces, thermal stability. So you get more balanced performance, whereas some of the others might have a little stronger performance in one area but be very weak in another. So some current coating applications where we find this polyamide technology to have good utility are in things like industrial metal coatings, wood coatings, things like flooring, furniture, cabinetry, as well as masonry flooring systems because of the features and benefits this technology provides. Things like the high levels of hardness and scratch resistance, excellent chemical and water resistance properties, great film clarity, and overall durability. In comparing the solids between your waterborne acrylics and your polyurethanes, you see some distinct differences in that the acrylics tend to be higher in solids, more in that mid 30s to mid 50s range. So typically higher in solids, but generally softer and lower in performance compared to the polyurethanes. Whereas the polyurethanes typically are lower in solids, more in that mid to upper 30s range, generally harder and higher performance. And then we have the polyamide polyurethanes based on this unique chemistry that Lubrizol developed, the polyamide polyols. And with this, we find the ability to deliver higher solids resins that are very hard and offer the highest level of performance. So we are now able to push that solids upwards of 55% for a polyamide PUD. Now that we have kind of a general overview of polyurethane dispersions and you have a little better idea of what we mean when we say polyamide-based polyurethane, I want to shift gears and get into talking now about the high solids polyamide-based PUD and talk about some of the features and benefits this technology offers, and then show you some comparative data of how the high solids PUD performs relative to your more traditional lower solids PUD and then a high solids commercial product that we benchmarked against. So in terms of some of the features and benefits, this product is supplied at greater than 50% solids. It's a waterborne, self-cross-linking, NMP-free resin that enables you to create greater than 40% solids coatings. So being supplied at over 50% solids can translate to some cost savings from shipping and storing less water when you're buying the resin. That higher solids also enables you to formulate higher solids coatings, ultimately enabling you to put down greater film thickness per coat. So for the contractor, that can reduce the total application time by eliminating the number of coats required to get the desired appearance or performance properties. We find this resin to offer fast drying properties, which again can help the contractors to get the job done faster by reducing the amount of time required to recoat. Because of the high solids, it also has the ability to be formulated at lower VOCs. There's less coalescent demand, allowing this product to be used in more VOC restrictive regions. We found that this product has a 35% bio-based carbon content, so we had it analyzed by an independent third-party testing laboratory, and of the carbon content in the resin, 35% of that was derived from bio-based sources or carbon that was less than 14 years old, so contributing to sustainability. This product is very easy to formulate with, offering the formulator greater flexibility and manufacturing ease that's compatible with a wide array of additives and different coalescing solvents and plasticizers. And as we saw in some of the earlier slides, some of the features and benefits of this polyamide polyol chemistry, this product offers things like outstanding abrasion, chemical and water resistance, hydrolytic stability, and thermal resistance, ultimately leading to long-lasting durability and appearance. One of the challenges with making higher solids resins can be trying to keep the viscosity within a normal range. And what we see here with the high solids polyamide polyurethane is we were able to push the solids higher, but to maintain a very low viscosity of less than 500 centipoise, much in line with a number of our other PUDs in our portfolio. And in this chart here, we're looking at formulated resin viscosity. So these would be formulated clear coatings made from the various resins. And then we're also comparing against a commercial high solids benchmark product that we bought off the shelf at a big box retailer. So the blue bubble is your traditional lower solids polyurethane coating formulated at around 30% solids, and you can see very low viscosity at 50 centipoise. Then we have the green bubble, which is the high solids polyamide polyurethane, formulated up over 40% solids, but yet at a very low viscosity of 120 centipoise. And then we have the commercial benchmark product, the red bubble up at the top of the chart. And so that's more formulated in the mid-30s range for solids, but you can see here significantly higher in viscosity at over 6,600 centipoise. And we'll see on the next slide kind of how that high viscosity can impact the overall application and appearance properties. So now when we take a look at the impact viscosity has on application, we can see in the top picture that the commercial high solids polyurethane that we bought off the shelf that was up over 6,000 centipoise in viscosity, that that the high viscosity led to some challenges when trying to apply the material. We can see the material had noticeable brush strokes and just kind of a very non-uniform, non-desirable finished appearance on the wood. Whereas in the bottom picture, we have the high solids polyamide-based polyurethane material that was formulated up over 40% solids, but maintained its low viscosity. And we can see a very nice uniform appearance, very high gloss, good clarity, and a very desirable appearance. In addition to the viscosity challenges, another potential issue with the higher solid systems can just be overall formulation stability. And in this case here, we're looking at accelerated heat age oven stability at 49C or 120F. And here we're comparing the commercial high solids polyurethane benchmark to our formulated high solids polyamide polyurethane coating. And the picture on the right, you can see there after just 3 days at 49C, the commercial high solids material has pretty much solidified, whereas the high solids polyamide polyurethane remains completely fluid and pourable. And then in the data chart, you can see, again, with the commercial product, we started out at over 6,000 centipoise viscosity. And within just a couple of days, it had completely solidified, whereas the high solids PUD remains stable and very low in viscosity for the 4-week duration of keeping it in the oven at 49C or 120F, having very good package stability. In formulating with the high solids polyamide polyurethane resin, we find that it has broad compatibility with a variety of different coalescing solvents, humectants, plasticizers, and additives. And in this study here, we're looking primarily at a number of different solvents and plasticizers. And you can see here in this chart, looking at film formation at 250 grams per liter, we're kind of looking at compatibility and looking at the respective gloss values and haze values down in the yellow bars on the chart. So the lower the yellow bars, the less haze, the better the clarity of the coating. And you can see some of the solvents and plasticizers have more of a thinning effect, very good compatibility with the resin. Some of them tend to swell the resin a little bit more. So you see some that are listed in green that say swell. So although they swell or build some viscosity, doesn't necessarily mean they're incompatible, but they could lead to some potential stability challenges. And then we see some that are in yellow that maybe are a little less compatible. And then the only one in our studies that we found to be really incompatible with the resin was the PPH solvent. But ultimately, the solvent, plasticizer, and additive selection is critical to get the overall best balance of properties, maintain that low viscosity, and get the lower VOCs. So while we looked at 250 grams per liter formulation here, we have pushed the VOCs down to around 170 grams per liter when using some plasticizer. I mentioned earlier in the presentation that one of the features of this high solids polyamide polyurethane was that it was fast drying. And in this chart here, we see when comparing against the traditional lower solids polyurethane in blue, and then the commercial high solids urethane product in red, that the high solids PUD really does have fast drying properties at less than a half hour being dry, whereas the traditional system is upwards of 2.5 hours, and then the commercial high solids urethane is closer to 3.5 hours. So significantly shortening that dry time, giving the contractor the ability to recoat quicker, get the job done sooner, and then also to give you earlier property development and quicker return to service. And in some applications, if that dry time is a little too fast, this resin is quite flexible you can slow that dry time down with the addition of some things like some humectants or glycols, or even just adding a small, like 1 or 2% of water if you were formulating up around 40% solids. If you drop the solids down a percent or two, you can also increase the open time as well to kind of dial that in for your particular application. One of the big advantages of the higher solids resin system is the ability to formulate a higher solids coating, and ultimately you're putting down greater film thickness per coat, ultimately leading to reducing the number of coats required, allowing contractors to get the job done faster. And in this example here, we're comparing a traditional polyurethane clear system formulated at 30% solids to the high solids polyamide-based polyurethane formulated at 43% solids. And what we can see is that we're effectively putting down more material in each coat ultimately. And so that after 1, 2, and 3 coat application, you can see with each subsequent coat, we're putting down more and more film thickness so that after just 2 coats of the high solids material, we've in essence put down a greater film thickness than 3 coats of the traditional system, ultimately allowing you to reduce a coat. So when we compare abrasion resistance of these different polyurethane systems, we see that the high solids polyamide polyurethane in just a 2-coat application gives the highest level of performance of the 3 systems evaluated here. And in this test, we're coating out wood panels and abrading the surface using CS17 wheels with a 1,000-gram weight load, and we're recording weight loss every 250 cycles. And so in this particular test, the lower the number, the better, because you're retaining more of that film as you're abrading the surface. And what we see sometimes is that materials that have very good hardness or high coning values, that they correspondingly tend to have poor abrasion resistance, that when you abrade the surface, more of it wears away. So you'll have a high coning, but you'll also have a high Tabor number. And with the polyamide technology, we find that you can have very good hardness values, but correspondingly have very low Tabor numbers, so good abrasion resistance as well. And so we see that we have pretty comparable performance in just a 2-coat application with the high solids material compared to the 3-coat system, and significantly higher performance when compared against the commercial urethane high solid system that applied in 2 coats, where it has upwards of over 250 milligrams of weight loss, so significantly poorer abrasion resistance compared to the polyamide technology. I mentioned on the last slide when we were looking at the Tabor abrasion performance that sometimes when you have materials that are hard or have high coning values, that they correspondingly have high Tabor numbers or poor abrasion resistance. And what we see here in looking at 7-day coning hardness, this is tested according to ASTM D4366, that the high solids polyamide polyurethane with, again, comparing 2 coats to a 3-coat of the traditional polyurethane system, at just 2 coats has very good coning hardness, upwards of 80 oscillations. And for having the good surface hardness, it has the very low Tabor number. So you get that balance of good hardness, but very good abrasion resistance as well. Similarly to the 3 coats of the traditionally lower solids PUD. And then comparing that against the commercial high solids benchmark, this product, we see it has much lower coning hardness, so it's a much softer material, and it also doesn't have very good abrasion resistance, that it had the highest Tabor numbers of the 3 samples tested. So again, we're able to achieve excellent hardness in just a 2-coat system. Another test that we commonly run, especially for wood floor coating applications, is black heel mark or scuff mark resistance, where we intentionally strike the surface of the coating with a hockey puck, and we look at that black mark that's left on the surface and how easily it can be removed with just some mild cleaning with a cloth dampened with water. We're not really aggressively scrubbing it or using any type of cleaners, but we're seeing, can that scuff mark be removed, and then we visually assess the panel on a 10-point scale, with 10 being very good, 1 being bad. And we can see here when we compare the 3 different systems that just 2 coats of the high solids polyamide polyurethane gave the highest black heel mark resistance, coming in an 8 out of 10, followed by the traditional polyurethane system, in this case a 3-coat system, coming in at a 7. So again, being able to deliver higher performance in 2 coats than the 3-coat system, and then compared against the commercial high solids urethane 2 coats, significantly higher performance, that the commercial product came in at a 3, with significantly more marking that remained on the surface. When we compare the 60-degree gloss values of the high solids polyamide PUD versus traditional solid systems, we see that the high solids resin is capable of delivering very high gloss values, much in line with the traditional PUD as well as the high solids commercial benchmark product. And here we see the 60-degree gloss for all 3 products coming in at just over 90 units at 60 degrees. So delivering very high gloss but also having the ability to be matted down with some surface modifier to get the gloss down if you wanted more of a satin or a low gloss finish as well. When we visually compare the appearance difference between the traditional lower solids polyurethane to the high solids polyurethane, you can really start to see how you get that better appearance development and fewer coats. In this panel here, we have your traditional system on the left with 1 and 2 coat applications. And then on the far right, you have 1 and 2 coats of the high solids polyurethane. And especially when you look at the 2 coat application, you can really see how the 2 coat high solids, the gloss development and the way that the coating pops and really stands out compared to the 2 coats of the standard polyurethane, where with that one you might need a 3rd coat or more to develop similar appearance. Here we're comparing the chemical resistance between these different polyurethane systems, and in this particular case we were looking at the MFMA, or Maple Flooring Manufacturers Association's chemical resistance test on wood panels, and there's a variety of different chemicals you can see here with varying either 1 hour or 4-hour exposure times, and then being rated after a 1-hour recovery period. And so here again, we're comparing 3 coats of the traditional polyurethane system to just 2 coats of the high solids polyamide polyurethane, and then 2 coats of the high solid commercial benchmark product. And in this spider diagram here, the further out to the outer edges or more touch points you have out there, the stronger the performance. So this would be on a 10-point scale, a perfect 10 rating. And you can see that for all these different various chemicals tested, the high solids PUD with just 2 coat application gives you very solid performance and very good resistance properties kind of across the board. So just to summarize or kind of recap on some of the features and benefits we looked at in the presentation. So this high solids polyamide urethane resin is, again, a waterborne, self-cross-linking NMP-free PUD. While it has built-in self-cross-linking functionality, it does have the ability or functionality to be externally cross-linked and made into a 2K system if that is desired. But very solid performance in a 1-component system. And again, just to kind of recap on some of the features we saw here throughout the presentation is that it has the fast drying capabilities, giving you less dry time and the ability to get the job done sooner, being able to recoat more quickly. And being higher in solids and the ability to formulate higher solids coatings translates to thicker films and the need for less coats to get both the desired appearance and the durability properties. With that higher solids gives you the ability or flexibility to formulate lower VOC coatings. And again, just being able to kind of overcome some of those challenges of sometimes pushing the resin solids higher and higher of package stability and viscosity. We see here with the high solids polyamide polyurethane that while coming in around 50% solids, we're able to supply that material at a very standard or low viscosity. Very stable, both the resin and the formulated coating, both ambient and when accelerated heat age stability testing was done. And again, from just the being based on this polyamide polyol chemistry, we see better properties, as we saw in the presentation, delivering very solid performance. Additionally, in a 2-coat as opposed to a traditional 3-coat system, so giving very good performance with fewer coats, and then delivering on that ability to for high gloss in those applications demanding a very high gloss, high clarity application. This coating or resin can be used both clear, or it has the ability to be pigmented as well, and it can be, as I mentioned earlier, with some surface modifiers or matting agents, you can bring the gloss down for a range of different finishes. And I'd just like to take a moment to say thank you and acknowledge a number of my colleagues who were instrumental in the development, testing, and commercialization of this high solids polyamide-based polyurethane. I'd like to thank you again for your time and attention and the opportunity to present on our high solids water-based polyamide polyurethane technology. If you have any additional questions or if there's any specific applications you'd like to further discuss, please feel free to reach out to me either by phone at 440-292-7562 or via email at eric.broz@lubrizol.com. Thanks again.